Now let's consider the compression. For the reversible case, we would just start adding 1 grain of sand at a time. This would slowly increase the pressure outside, which is P external, plus the pressure due to the sand, and the piston would slowly go down and the pressure inside the system would increase. The result will be that we would follow this exact same curve on our way back, and so the area under the curve is going to be the same. But in the compression, the signs are going to be the opposite. So in the compression, the work is going to be positive because we're doing work on the system. So the work is equal to positive area B, and the heat is equal to negative area B. So if we think of this as a cycle going from 1 to 2 and then back to 1, so back to our starting position, then we can see that the net work would be the work of the expansion, negative area B, plus the work of the compression, positive area B, so the net work is 0. For the heat, we have at the beginning for the expansion, we have area B is the amount of heat flowing into the system, and for the compression, we have area B is the heat flowing out of the system. So the net heat flow is 0 for a reversible process. Now, how does that compare to an irreversible compression? For the irreversible compression, we can imagine that to compress this piston back down, we set a big mass on here with mass M. When this piston drops back down, the mass is going to drop down and it's going to lose potential energy equal to mgh is its potential energy loss. That loss of potential energy is the energy which is gained by the system as it returns to its starting point. We can see how this mgh relates to P delta V by examining the formula. So if we were to have pressure times the change in volume, well, pressure is force per area, and volume is the area of the piston times the change in its height. In this case, for a mass, the force is equal to the mass times gravity over the area times area delta H. So we can cross off these A's and we can see that P delta V is equal to mg delta H. It happens that this is equal to P1 delta V. So it's like we're going from V2 to V1 with a constant opposing pressure. So this area here we'll call area C, and that is the work associated with the compression. So for the compression here, the work is equal to positive area C, and the heat is equal to negative area C. We can see quite clearly that area C is larger than area A, and so in the cycle, thinking of going from 1 to 2 and back to 1, the work done by the system in the expansion is less than the work done on the system in the compression. This makes sense because in the expansion, we are always lifting against a low pressure, whereas in the compression, we're pushing against high pressure. So the surroundings have to do more work on the system than the system did on the surroundings. Now we can look at the heat. The heat in the expansion was equal to area A. So a small amount of heat, area A, flowed into the system in the expansion, but during the compression, a very large amount of heat, the negative area C, flowed out of the system. This means at the end of our cycle, the surroundings are hotter than they started. They've had heat flow out to them. Even though we have restored our system to its starting state, the surroundings are different. They're hotter. So that's the difference between a reversible versus an irreversible process. In a reversible process, we can go back along the exact same path that we took to restore a system, whereas in an irreversible case, we need to take a different path, and the result is that we can't restore both our surroundings and our system simultaneously.